6 tutorial group. So I request all of you, please join your tutorial group. And I have also posted the tutorial sheets, two tutorial sheets, tutorial sheet 1 and 2. So you should try first. And your TA, so when you join your group, and then your TA will contact you and fix a date and time which is suitable for you. So you can choose any time, any date which is suitable for you. So there is no restriction on a time limit. So if you want at night, at morning, even in the weekend, then you can freely um, suggest your timing to your tutor. Huh. So Rehan Khan. So where you have shared tutorial? So I have shared here only this MS Team group. I have just posted the tutorial sheets 1 and 2. Also, I will post it or everything in the Impartus as well. So everything I will post in MS Team group as well as in the Impartus. Till now, I did not I have not post anything on the Impartus, but I will do that one as well. Okay. So what I can do, I can should start today. I share my screen first. No, no, no. So we have just created the tutorial pages only on Monday, and students are joining. So tutor did not contact. So tutors will be contacting soon. Okay. So but I request you everyone should join your group and also ask your friends, because I just checked that tutorial groups. So I have seen there are around 20, 22 or 17 number of students, but we have each group have around 34, 35 students. But I don't know where are the remaining peoples. So only two groups I have seen around 27, 28, and some groups have only 17 or 18 students. So they should join. Okay, so if you have not joined yet, you should join first, and also you encourage your classmates to join as early as possible so that tutors can contact you and decide the time and date.
Join where, sir?
Join the tutorial groups.
Which on WhatsApp or something? I don't know.
No, 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 in the MS team. So I have sent you one email. Also, I have posted here. So you have to join your tutorial group by a code. That code is given.
Wait.
Okay. I can show you where code is given. So this is our MS Team group, right? So here I send the message. You should look at the message in the MS Team.
Yes, yes, yes.
Okay, this one and this is. So if your name is not listed, then you can ask me.
Okay.
But if you registered earlier, then your name should be there. So if you are a new registered student, maybe after the changing the branch, then your name will not be here. Then you can ask. Then I will tell you who is to join. So what is my idea? To distribute all the students equally in each group, so that it will be helpful for us to conduct the tutorial and also take the exams. So every tutorial will be held on those groups, and also you will give exams through that group only. Okay. And in case of any problem, you can contact me. Don't worry about that. Okay. Right. So can you see this white screen? Yes, right?
Yes,
Yes.
sir.
Yes,
Okay.
sir.
So as I told you that this portion of or this logic, you can say, that is very easy. You have already seen in the first lecture, we have defined something and that is very easy, right? So I know that this is very easy. And also this lecture will be also very easy. So last time I stopped at conditional statement. Now today I start with few more definitions. So first one is compound proposition. So these are just names. It is better to remember those names. So what are the names of these propositions? Because this is the main part of the logic. And also if you don't want to remember something, then you also skip that. But there are something which you should remember. That's I will mention. For an example, there are some laws. You have to remember the names of the laws. But it is always better if you can remember all of these names. For an example, that compound propositions, conditional statements, everything. Okay. So I wish you should remember everything. But if you want to skip, then you can skip as well. But not all. Okay. So I start with this one. So what is a compound proposition? So I have defined proposition last time. So that compound proposition is just again a proposition which is formed from existing propositions. So this is just a new proposition which are formed from existing propositions. So using logical operators. Okay, so these are called compound proposition. So in particular, if you take any proposition P and Q, trivially you can say them compound proposition. Okay. And if you have P and Q, two proposition, then if you say that new proposition say P implies Q, it has a truth value, right? So this is also a proposition. Now this is called a compound proposition in general. Okay, because this is a new proposition formed by P and Q using logical operator that implies. That's mean if P then Q. Okay, so this is called a compound proposition. And in particular, you can say P as also a compound proposition. You are doing nothing, right? You are not using any logical operator, or you can say we are using just identity operator. That's all. Okay. Now we know that conditional statements, and there are three more definitions related to the conditional statements. Now these definitions are converse. You already know this one when you have seen the proofs of many theorems. Now you will see what are they actually. Okay. So what is a converse of a statement? So you know what is this, right? But here also we will discuss this in terms of logic operator. Okay, I should minimize this. Okay. So first of all, let P and Q be two propositions. Okay. Now then the converse of the, so we generally say converse of the conditional statement. Okay. Of the conditional statement P implies Q is just Q implies P. Okay, or you can say that if P then Q, the converse of the conditional statement if P then Q is if Q then P, or in short P implies Q, the converse of P implies Q is Q implies P. Okay, you know this one. Now this is just a definition of converse. Now you similarly you can define contrapositive. So we will see all of these, that converse, contrapositive, inverse, we will see all of this when we see how to prove a theorem. Okay, so here in this course we will discuss how to prove, how to write a proof, and there we need this concept, that converse, contrapositive, inverse, all of this. So these terms are very important. So as I told you at the beginning, that if you don't want to remember all of these terms, then you can skip, but you should not skip these parts. So you should remember these terms. For an example, converse, contrapositive, inverse, these are the very important terms in this logic part. Okay, so you should remember this. So one is converse, another one is contrapositive. So you have already used actually this contrapositive arguments. So let P and Q be two propositions. So then the contrapositive of the, or you can say that contrapositive statement of the conditional statement of the conditional statement P implies Q. Do you remember what is the contrapositive statement? This is
Negation P implies negation. Negation
right,
Q implies negation P.
right. So it is not P implies not Q. Okay, or you can say that negation of Q implies negation of P. Right. Now this is an interesting part, is that you can easily verify that I have defined that equivalence one, right? No, I did not define it, I think. Okay, so we will see later that equivalence one, and then we will see that this one, that is P implies Q and not P implies not Q implies not P. Both statements are same actually. Okay, so they are logically equivalent. We will see after defining that equivalent one, we will see that both are same. So the conditional statement and the converse of that statement, they are not same, but here the statement P implies Q and negation of Q implies negation of P. Both statements are actually same. We will see that. So another one is inverse. Okay, so here you you have to remember three concepts. One is converse, another one is contrapositive, another one is inverse. The inverse. Am I audible now? I think I got disconnected. Hello.
Yes, sir, you are audible. Yes, sir, you are
Oh,
audible.
okay, thank you. So then the inverse of the conditional statement P implies Q is that inverse is mine A. The negation of P implies negation of Q. So that is the inverse of P implies Q. Okay, so again, I should mention you that, so this part is very simple, but you should not feel bored on this part because this is your chance to grab the marks. So when we teach the graph theory and combinatorics, that part is little bit maybe difficult than this. So it might happen that you get little bit less marks on those portions, that combinatorics and graph theory. Okay, so this portion is easy, though it is very simple, but still there are many students who did some silly mistakes. So last time I have taken this course, I have seen that many students uh, did not get full marks on this portion, that is logic portion, because they did some silly mistakes. So you have to be careful on this, though it is very simple. Still, you have to be very careful on this so that you have not done any silly mistakes. Okay, and then only you will get a good marks in this portion. So if you get around 25 out of 25 in this portion, then that will be a big advantage for you in your total marks. Okay, so I just want to say that though it is very simple, but still you should not feel bored and you should read carefully so that you can get full marks in this portion, because the other portion, combinatorics and graph theory, that portion will be little bit difficult. So not everyone will get full marks, definitely, but here everybody can get full marks. Okay, so then I define that by conditional statement. So we have already defined conditional statement, that's mean P implies Q, right? So that name suggests already. So what is a biconditional statement? That's mean P implies Q and Q implies P. On the other way, you can see that P if and only Q. Okay. So I should write the definition. So let P and Q be two propositions. Then the biconditional statement so we will denote in this way, that is double arrow. That's mean P implies Q and Q implies P, or P implies Q and as well Q implies P as well. Okay. So P implies Q and Q implies P as well. Now this is the statement. So you can see the proposition. P if and only if Q. Okay. So that's mean. So I can write the truth table, then it will be clear to all of you. So the truth table, and note that the name is a truth table. So that does not mean that it is always true. Okay, truth table means that table contains true and false. So it might happen that so it has a one entries true and false, but the table is called truth table. Okay, so this is just a name. So don't be confused with the true with the truth table. Okay, so truth table is just a table and it contains true and false. Okay, so the truth table for the biconditional statement is, so again we have 4 rows because we have only P and Q, right? So we will have 4 rows. So this is 1, 2, 3, and 4. So this column will be P, this column will be Q, and this is P if and only Q. So that's when if both are true, then that will be true. Okay. Now if this true, this false, then Q implies P, that is true, but P implies Q, that is not true. So therefore it is not a if and only condition. So therefore the truth value will be false. Similarly, if this is false, this is true, then P implies Q, that will be true, but Q implies P, that will be false. So therefore P if and only if Q, that is actually false. So this is false. Now if both are false, then P implies Q, that is false because your hypothesis is false. And similarly Q implies P, that is also, sorry, P implies Q, that is true because your hypothesis is false, right? And similarly Q implies P, that is also true because your hypothesis, that is Q, is false. So therefore P if and only if Q, that statement is true. Okay. So this is the biconditional statement. And fine. Similarly, you can do that. So now we can see one problem on the truth table. Okay, maybe we first define that equivalence and then we can define that. Okay. So first we define now tautology. Okay. Now this is also one important term. You should not forget this term. Okay. Because you have to use this term everywhere. So a compound proposition is called tautology if if the truth values are always true. Okay. So if you have a proposition whose truth value is always true, then we will call that proposition by tautology. Okay, this is a name, and that the reverse of tautology is called actually contradiction. That's mean I will define that one as well. So a compound proposition which is always false. So this is not a negation of the tautology. Okay. So this is just in similar way we can define this contradiction as well. So a compound proposition which is always false is called a contradiction. So in the same spirit of tautology, we defined contradiction. And now the main important part, that is logical equivalent. So two propositions P and Q will be called logical equivalent if they have the same truth values. Okay. In other words, we can say that two propositions P and Q are called logically equivalent, or you can say logical equivalent if that biconditional statement P if and only Q is a tautology. In other words, that P if and only Q is always true. Or you can say that P and Q always have same truth value. Okay. And it is denoted by that symbol, equivalence symbol, this one, 3 parallel line. Okay. Q. So that's mean P is equivalent to Q. Okay, now we can solve few problems. So these are all the definitions. We do not have more definitions here. Okay, now first we will solve few problems on the truth table. Then I think you will feel happy. So first I will solve one and then I will ask you to solve one. Okay, so you will solve and then you just take the photo and upload here. Okay, so I think all of you have pen and copy with you, right? Even I don't want from all of you. So even if only one or two can give me the solution, then also it is fine. But you should have pen and copy with you. Okay. So first we can say that construct the truth table for this one, that P or negation of Q implies P and Q. This one. Now again, you can see that when you have only two variable, so you need only 4 rows, right? Only 4 rows are sufficient here. Okay, so this is my 1, this is 2, and here we will have 3, 4. Okay, and here I can write P, here I can write Q. Since we need minus Q, so we can write here minus Q, then P or minus Q, then P and Q, and then this one. So I can write here P, Q, we need minus Q as well, P or minus Q or negation of Q, P and Q, and the statement is P or negation of Q implies P and Q. Now another again another rule actually for this course. So this one very simple. You also know that this is very simple. But when you write in a exam, okay, see you can verify this by without using pen and paper. That is fine. But whenever you are asked this kind of problem during examination, you should write clearly. Okay, I know everyone. So last time I have seen many student uh, could not did not solve properly, and they just say that okay, we know I know that portion, so I did not write. But during examination, you should not do that. Whatever you write, you should write clearly. Otherwise, your TA or when I will check the question answer sheet, then we will deduct marks. And then you cannot complain that okay, no, you know this is very easy, so I did not write. So whatever, if it is very easy, still you should write each and everything. Because this is the portion of logic only. And you have to write in a logical manner. For an example, whenever we are using truth table, you should use true and false. You should not use 0 and 1. Though it is clear, but you should not write. Because generally we use T and F, not 0 and 1. Okay. Anyway. So now we will find a truth table for this one. So we use all the term, that is it is true, false, right? Oh, sorry, true, we can choose first. True, true, false, false, true, false, false. So these are the all possible choices for P and Q. Okay. Now since Q is this true, so this is minus negation of Q, so this is false. Since this is false, this is true. This is true, this is false. Since this one is false, so we have true. Okay. Now P or minus Q. Okay, so P or minus Q. So we have here true or false, right? So we have two. Here true or true. So this is true. Now we have false or false. So this is false. Now again false or true. So this is true. And what is P and Q? Now this is true, true. So therefore true. So this is true, false. So true and false. So this is false. Now again it is false and true. So this is again false. So this is also false and false. So this is false. Now this implies this. So true implies true. So therefore that value is true. Now true implies false. So the value is false. Now false implies false. So the value is true because the hypothesis is false here. So this is true. And again true implies false. So this is false. So this is the truth table. Okay. So this is very simple. Now I will solve another one for you. So the question is, so you can write problem. Show that my negation of P or Q is logically equivalent to negation of P and negation of Q. Okay, and this equivalence relation is it has a name, and this is called De Morgan's law. Okay, so this. Now again, so that's when you have to show that this one and this one have the same truth values for all choices of P and Q. Okay, there is a question. I missed that. Is it equivalent to Q? Which one? Oh, this one. Right, yeah. So Q and this one have the same truth values, right? So true, true, false, false, true, true, false, false, right? So they are equivalent then. Right, good observation. Thank you. I also missed that one. So good that you already know all of this. So this is called De Morgan's law. Now again, you can easily prove that. That proof is very simple. So this is just a manually you can do and you will get the answer, right? So this is very simple. So still we can do that. So first of all, again, we can choose this is P, Q, right? And then P or Q. And after write P or Q, we will write negation of P or Q. So this portion will be done. Then we will write minus P, negation of P, then negation of Q, and then negation of P and negation of Q. Okay. And then we can write that final statement. That is, we need to show that equivalence, we need this one. Here we can write this. So that will be always true to show that this. So this portion. So that's when it is sufficient to show that this and this have the same truth value. Now that is very simple. Again, we can write all possible values. True, 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 false, false, true, and false, false. Then that will be your true, true, true because at least one of them is true, right? And this is false. And the negation will be false, 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 true. So the value of this will be false, 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 true. Okay. Now check this part. Now that will be false, false, true, true, and that is false, true, false, true. Now this is since it is and one, so false and false. So this is false, false and true, then again false, true and false, again false, true and true, again true. Right. Now you can see that this and this have the same truth value, right? So false, if and only false, so this is true, this is true, this is true, this is true. So therefore this is a tautology, right? So it has the values on that has only values true. So this is a tautology. So therefore this is equivalent to this, and this is called De Morgan's law. I should mute everyone, otherwise it is little bit disturbing. Right. So this is very simple. Now, do you want to try? Now, just try this one, and then those who do solve this fast, please send the picture here. Okay. Then I will share this with the other people. So P implies Q equivalent to negation of P or Q, and it has a name actually, and this is very useful. This is implication law. Okay. Now can you quickly solve this? Just quickly solve this. And send us the picture. Okay. So I want to see who also solved this one faster than others. I can write here another one.
So can you share the screen?
No, I cannot. No, I am not sharing the
No,
screen.
can you do the question?
Oh, okay, okay. Okay, someone also tried this one. And someone this. Okay, so there are three questions. So sum of one, do the first one, sum of one, do the second one, sum of one, do the third one, and just share the share your picture. Okay, so take the photo and upload here. Oh, everyone is solved. Okay, got one. So this has the same truth value, this and this. So true, true, false, false, true, true. Okay. Oops. Okay, it is fine now. Someone solve the second one. Second and third one. Now here you need eight, eight variables. Okay. Good. So many one have solved this one. Okay, anyway, so now you can stop. So now we will see some more definitions. So this is good that you people are learning very fast. But I know that this is very simple for you, right? Fine. Okay, so we have already discussed about the De Morgan's law, and this is called implication law. Okay, so we will use these laws. Okay, and this has also name, and this is called distributive law. This one, the second one. So this is called distributive law. Okay, fine. Now there is okay, there are some few more law. So one is commutative law. That is very simple. You already know that P or Q is equivalent to Q or P. You don't need to prove this one because this is very trivial. Right? So this is called commutative law. So there are two types of distributive law. So one you have already proved. So one is P or Q and R is equivalent to P or Q and P or R. And another one is P and Q or R is equivalent to P and Q or P and R. Okay, and also you have associative law. Also, you know, this is also very simple. So P or Q or R. So you can just shift the bracket. This is equivalent to, and also you can do this for the end as well. Okay, so this is very simple. Now using these laws, can you prove this? Now again, this is for exercise for you. I will not solve it. So example, P or Q implies, sorry, P and Q implies P or Q is a tautology. Okay, so before going to prove up this one, I just want to define one notation. Okay, so one notation. So a proposition which is always true is also denoted by only T. Okay, so instead of a proposition, instead of P or Q or R, you can write only T for a proposition if the value is, if the truth value is always true. Okay, and similarly, a proposition which is always false is also denoted by F. For an example, if you take, so if you take T, okay, and P, now that is equivalent to P. You can verify this one. That is very simple, right? And if you take, say, false or P, then again this is equivalent to P. Okay. Now if you take P or T, so that's when it is P or true, right? P or T, her T is always true. So therefore the truth value is always true. So that is equivalent to T. That's when the truth value of this one is always true. And if you take similarly, say P and F, that's mean P and A's proposition which is always false, then that is always false. Okay. I got a message. Which one? What is this? 4 implies 1 implies.
Sir, this is irrelevant right now.
Okay. Right. Okay. So you can use this notation T. Right. Now just quickly show, can you solve me this one for me? So this implies this is a tautology, and remember that you cannot use the truth table. You have to use the laws only. So you can use different kind of law and you prove that this is equivalent to T. Okay. So you cannot use the truth table. Just quickly solve it. Because by using truth table, this is very simple. We have already seen many examples of this one. Now solve it without using any truth table. I already got one message. Okay, no, this is the previous one. Right. So whenever you have this, you have to this equivalent to this. So, but remember that you have to write which law you are using. Okay, you have to write that. So here you are using that implication law. You have to write the name. Whenever you writing during exam, you should mention that. Okay. So here you are using this to this. You are using that implication law, right? Now this to this you are using De Morgan's law, right? And then you are using the commutative and associative law together. Right. So you people are very smart. See, if you write these solutions, then you will get maybe one or two less marks because you cannot use that symbol. Implies. Okay. So you are proving this implies this, but we need this implies this as well. So you have to write here that equivalent symbol. So this is a silly mistake which you will do and you will get one or two less marks. So this type of silly mistake generally shouldn't do during exam. Okay. So you should not write. I know that you know everything, but the problem is that you have to write precisely. Otherwise, your marks will be deducted. Okay. So here you should not write that implies. So you should write here equivalent. For an example, you can see here. He has written that equivalence one. Good. Okay, fine. Now we can move forward. Okay, so let's define some more definition. So there is another term that is predicates. Again, this is not very important. You can forget that term, that name. So what is a predicates? So first of all, let Px be a sentence involving the variable x. Now then the term that P, that is just kind of one kind of function, then P is called the predicate. For an example, suppose your Px is say x greater than 3. Okay, so Px is the statement that x is greater than 3. Then the predicate P is is greater than 3. Okay, and x is the variable. Okay, so here Px is a sentence Okay. So here Px is a sentence, right? And P is called the predicate and X is the variable. Okay. But remember that here Px is not a proposition. Why? Because you cannot say that Px is true or false because of the X, because you do not know what is X, right? So here Px is just a statement. It is not a proposition, and Px and P is called a predicate. But if you give a values of X, then it will be a proposition. For an example, Px is not a proposition, but P1, P2, P3, P4, etc. These all are propositions. But you can write it Px is not. Okay, so Px is not a proposition, but for each values of X, P this one is a proposition. And now here you can see that you can also find the truth value, right? Here P1, P2, P3. Now these are the propositions and their values are false, right? So these are the propositions and value is false. But P4, P5, etc. These are true. Okay. And this predicate involves more than one variable as well. For an example, you can have this kind of statement as well. So say Q x comma y, x equal to y plus 3. So here also Q is a predicate and the variables are x and y. So here Q is a predicate and x, y are variables. Okay, and here Q say 4, 1 is a proposition which is true. Which is true. Fine. Now you can forget this name, that predicate. This is not an important one, but you should remember that what do you mean by P1, P2, P3, P4, etc. Okay. Now we have one most important term. You should not forget that. So this is very important. So this is called quantifier. So this is very important. Okay. So you generally have three types of quantifiers. So first one is the universal quantifier. Universal quantifier. Okay. The second one is the existential quantifier. Okay, so these two are very important. And the third one, this is less important, that is called the uniqueness quantifier. So what are they? You are already familiar to this, and you have already used this one in your calculus course as well. Okay. So here we are giving the formal definition of this quantifier, which you are already familiar and you have already used this one. So first of all, the universal quantifier. So what is this? So the universal quantification of Px is the statement Px, or you can say Px is true. If you want, you can omit this term as well. It is not necessary. You can write only Px. Okay. For all values of x in the domain. Okay. And this is denoted by this term. That is for all x Px. This. So when we write that for all x Px, that's mean we are saying that Px is true for all values of x in the domain. Okay, so this is just a symbol and it means Px is true for all values of x in the domain. Okay, so you are already familiar to this. And similarly, we can define the existential quantifier. So the existential quantification of Px is the statement so there is an element x in the domain such that Px, or you can write Px is true. Okay, as I told you, you can omit this one. So you can stop here either on up to Px, or you can write Px is true. Okay, and this is denoted by so there exists x Px. Okay, so this is just a symbol. There exists x Px. So this means there is an element x in the domain such that Px is true. Okay. Now from this definition, you can find also the negation. So what do you mean by negation of this? So that is also simple. So you can say that. So first of all, we write. So for all x Px. Now when this proposition is true. Now this is true if Px is true for every x. Okay. And when for all x Px, this is false. When this is false, if there is an element x for which Px is false. So if you have only one element for which Px is false and for other value it may be true, then this is false because for all x Px that is not true. Okay. And similarly, you can say that there exists x Px is true if there is an element x for which Px is true. Okay, and when this is false, there exists x Px is false. So if Px is false for every x. Why? Because if Px is true for at least one element x, then this will be true, but this is false, right? So therefore Px is false for every x. So therefore you can easily see that, or you can also prove in terms of some language that negation of this one, that for all x Px, that is equivalent to there exists x negation of Px. Okay, and negation of there exists x Qx, this is equivalent to for all x negation of Qx. Okay, so these two are rules. So sometimes it is also called that De Morgan's rule for quantifier. But you can always use this. Okay, and one more thing. Now suppose your domain. Now if your domain has only finite value, or you can say that is a finite set, is a domain is a finite set, say x1, x2 up to xn, then for all x Px, this is actually equivalent to, or it is same statement as Px1 and Px2 and up to Pxn. Okay, and there exists x Px that is equivalent to Px1 or Px2 or Pxn. This. Okay, so okay, we can see one example and then we will stop. Okay, now see one example. So we have taken this example from the calculus course only. So write limit x tends to a fx equal to L in terms of quantifier.
Sir,
Huh.
sir, here which we have written in green, if your domain is a finite set, then there these are the only elements which we are considering, like x1, x2, x3 up to xn.
Right.
Right.
So x can take only x1, x2 up to xn, nothing else.
Okay, sir.
So that domain is very important. So yeah, we will see here. So for an example, write this in terms of qualifier and say f is a function from D to R. Okay. Now, do you remember how to express this in terms of quantifier? Do you remember the definition first of all? So limit equal to L.
So that epsilon, right?
Epsilon delta definition.
Uh, uh, for for every x greater than 0. Sorry.
Every epsilon.
For every x there exists epsilon greater than 0.
No, not for every x. It starts with for every epsilon greater than 0.
Oh yeah, sorry. For every epsilon greater than 0,
For
there
every epsilon greater than 0,
there exists
there
x
exists,
belonging to D.
no, there exists delta bigger than 0 such
Oh,
that
okay, sorry. I'm thinking of
Okay.
limit of sequence.
no,
Such
for
that
all epsilon bigger than 0, there exists a delta bigger than 0. Now such that
for
for
mod
all
of
x, for all x,
um,
for all x in the domain,
Hmm.
okay, whenever you have this, so 0 less than mod of x minus a less than delta, that will imply mod of f of x minus L less than epsilon. So that is the definition of this in terms of quantifier. Okay, so this is the definition of limit in terms of quantifier. Okay, now suppose we are saying that limit is not equal to L. That is the negation of this. Now negation of this. That is limit x tends to a fx is not equal to L. Then what will be the negation of this? Now we have just defined what is the negation. Now can you tell me what is the negation of this?
there exists an epsilon greater than 0.
Right. So for all epsilon that it changes to there exists epsilon bigger than 0. But tell me why we are writing epsilon bigger than 0? Because it is a negation, but why we are writing bigger than 0? Still, why we are not
Because
writing?
like if you do like double negate, like epsilon less than 0 is not even part of the domain. It will not even be. It doesn't matter. We don't care if epsilon less than 0.
Actually, here we are writing here this bigger than 0 belongs to D. That is gives the domain. So here when we use that quantifier and that negation, our domain will not change. Our domain will be same, and we will apply the negation only on the quantifier only. Okay, not on the domain. Domain will be always same. So the domain of epsilon is here positive real number, and here also it will be positive real number. That's all. Okay. So the negation will be there exists epsilon, and there exists epsilon will be changed to for
For
all
every delta,
for every delta bigger than 0. Again for
there
negation of this
exists
one
x.
will be there exists x belongs to D, and what will be the negation of this?
Uh, Wait, it'll be P implies Q is P and not Q.
Right. Why? Because by the implication law we know that P implies Q, that is equivalent to not P or Q. So minus negation of P implies Q, that is equivalent to, by using De Morgan's law, it will be P and not Q. Okay, so this will be 0 less than x minus a less than delta and not Q. That's mean f of x minus L, that is bigger equal to epsilon. This. So that's mean now in terms of logic, it is very simple to write. Now you can say there. So what do you mean by limit x tends to a fx is not equal to L? So that's mean there exists epsilon bigger than 0 for which for all delta bigger than 0 there exists x such that 0 less than x minus a, mod of x minus a less than delta, but mod of fx minus L bigger equal to epsilon. So even during the calculus course, I actually taught this one. So I also told there that whenever that um, the negation of this is not simple. That for all that limit fx is not equal to n. It is better to write in terms of quantifier first, then find the negation, and then write in terms of English language. Because otherwise, if you directly write in terms of English language, then it is not clear then how this negation is coming.
Right.
And yes.
So from the definition of De Morgan's rule for quantifiers, the
Hmm.
negation of for all x px is there exists x negation of px. So
Right.
for all epsilon positive, there shouldn't be there exists epsilon negative some this kind of thing because there is negation of px.
Right. Yeah. So what is when here we are writing in short, but you can write this is in this way that for all epsilon, okay, there exists delta such that for all x, and then you can write this. F of x minus L less than epsilon. Okay, so this is the actual statement, and then you can say that domain of epsilon is say 0 to infinity. Domain of delta is 0 to infinity, and domain of x is d. Okay, so this is just a domain, and then when you are applying your negation, then you will apply the negation only in this quantifier. So the domain will not change.
Okay, okay, sir. Okay.
Okay,
Yes, sir.
so that's why I told you that you should not be confused with this one bigger than 0. So when you are writing that epsilon bigger than 0, for all this is a for all epsilon bigger than 0, and this is the condition on the epsilon. Okay, that's when we are taking the domain of the epsilon. And if you have confusion, because here we are using epsilon bigger than 0, and here we are not using that one, so better to write in this way, then there will be no more confusion. Or you can write in this way but think in this way, because that this bigger than 0, bigger than delta, and d, these are denotes the domain of epsilon, delta, and x. But here this portion is not declaring any domain, so this is a condition. Okay.
Yes, sir.
Okay, good. Good that you are asking. You should ask this type of question, because otherwise there will be some confusions and maybe some students will not ask.
Sir, so the domains are not affected by the negation.
Right, right. Because we are considering the same domain only everywhere.
Okay, sir.
Because if you change the domain, then there will be no meaning of the problem. Because domain should be same. Okay. Now by this, when we say that limit x tends to a, f of x does not exist. When we say that, so we have already seen that this is the negation, that limit is not equal to L. So that was the definition, right? Now we'll say that the limit does not exist. That's mean if you choose any L for every L, this is not true. So limit does not exist means we can write in terms of quantify this one. For all L, there exists epsilon bigger than 0, such that for all delta bigger than 0, there exists x belongs to d, such that 0 less than mod of x minus a less than delta, and mod of f of x minus L bigger equal to epsilon. This. Okay.
Sir,
Right.
should we
Huh.
specify the domain of L as well? Or is
Huh.
it basically
But
understood that it
better,
should be real?
better.
Okay.
You can write here. Because we know that our limit can be real number only. It is better to write. Always means if you specify everything, then it is always nice, right?
Sir, here does the order matter?
Right. Here order matters. For an example, if you have say for all x, p, for all y, pxy. Okay. So this one. Then what does it mean? So that's mean here pxy is true for every pair x and y. So that is fine. So here you can change. This is same as for all y, for all x, pxy. Right? Similarly, if you have two there exist, then they can commute as well. But when you have mix, for an example, for all x, there exists y, pxy. This may not be equivalent to there exists y for all x, pxy. Right? You can just verify this one by taking pxy is a statement which is saying that px plus y equal to 0. Now then you can see that for all x there exists y, pxy. Now this is always true. So this is true, but that is there exists y for all x, pxy. This is false. Right? Why this is always true? Because for all x you can find y, you can take y equal to minus x. But whenever you choose a y, you cannot say that for all x you have x plus y equal to 0. You cannot say that. Because for each y you have only a single x. Right? So this is true, this is false. So therefore that order matters. Whenever you have combination of for all and there exist, then that order matters. Okay. Okay, I just forget to define. I think that uniqueness quantifier. I just define that one, and then we'll stop. The uniqueness quantifier. So that's mean it is saying that there exists a unique x such that px is true. So this is the statement, and it is denoted by so there exists. It is the denoted by unique. There exists unique x such that px. So this is the notation. And this means that there exists unique x such that px is true. Okay, so you should read from the book because I am following that book, strictly following that book. We can say that because everything you can find from that book.
So can you share these class notes, the one you have written today?
Yeah, I can share you, no problem. But I don't know. But this is the same thing.